All right, I want to go over a little more detail on projectile motion, but from the perspective of dealing with situations where acceleration is constant. So I'm going to put projectile motion here as our topic, but really we're dealing with constant acceleration. And you need to be sure to watch the kinetic videos where I talk about projectile motion in more detail. But in this situation, when we're dealing with constant acceleration, we are not going to deal with drag force due to air resistance. Okay. We're not going to, because then what we have is a situation where a projectile in the air is being acted on by one force, and that's the force due to gravity. And if I dealt with air resistance, I'd have to draw another force on here. But when we deal with a situation with one force acting on the object, we then use our Newton's second law, and we have the force due to gravity, which is a downward force, and that's a constant, constant, and therefore acceleration is also constant. And we know that when gravity is the only force acting on the object will accelerate negative 9.8 meters per second squared. And so I deal with projectile motion from the perspective of kinetics, where we deal with one force acting on the object. We simplify this equation to Fg equals ma, and that's a negative force because it's pulling downward on the object. And then we know that acceleration is constant. And knowing that, we can perfectly predict the kinematics. And we see that with our eyes. We see projectile motion with our eyes, and we can understand how to catch a ball. We can predict its motion, very simple. But the key with this next section or this video is we are not going to deal with air resistance as a force at this stage. We'll add that back in, and then when we do our Newton's second law, we'll have two forces acting on the object, gravity and air resistance, and we add up those two forces to understand the acceleration of the object, which would not be constant at that point because drag force is a function of velocity. All right, so this is the direction we're going to go in. We're going to deal with constant acceleration situations. We'll think about a projectile going through the air. All right, so let's start with our PVA of a projectile, and let's deal only with vertical motion in this starting place, because that's a lot of times what our eye is drawn to. All right, so I'm only going to concern myself with the vertical position, and I'll put meters here, versus time of a projectile flying through the air. Yeah, okay, I'll back up in just a second. And then we're going to do velocity, vertical velocity in meters per second versus time. And then acceleration, vertical acceleration, meters per second squared versus time. And I've got 0 here, 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 and then this is positive velocity, this is negative velocity, this is positive acceleration, this is negative acceleration. All right, so let's remember we'll deal with our convention of up is positive, and we can start sketching this PVA from any one of these plots. I'll actually start with the acceleration, because we know the moment an object is being acted on by the force of gravity, acceleration is going to be constant, and that constant would be negative 9.8 meters per second squared. So acceleration from the time that flight begins, let me try to write with a pen on that so it's not too big. Flight begins And then to the time that flight ends, the acceleration of the object when gravity is the only force acting on the object is negative 9.8 meters per second squared. And so knowing that, I can actually derive some of these other plots, but I still need a little bit of information. We don't actually know if this object is being dropped and speeding up, moving downwards at this rate, or if it's going upwards and slowing down at this rate, All right, we don't know that until we know something about vertical velocity. And so what we're going to do is actually break this problem into, let me draw out what we have here. If I go from position, and I'm going to draw these hash marks upwards, so these are all the same moments in time, and I track the entire vertical position, and let's say the initial velocity is some value that's going to project this object upwards, okay? And when we have some initial velocity, we're going to have this type of shape of curve, and this is vertical movement only. And we would call this shape, we would put a special name on this shape, and it's a parabola. It's also described as a second order polynomial, if you're interested in math. A first order polynomial is a straight line with slope m. A second order polynomial is ultimately one of the equations of constant acceleration we're going to derive. And when I have this parabola shaped like this, where the object goes up and is slowing down at a rate of negative 9.8 meters per second squared, and then it's moving downward, speeding up at this rate, then I have a velocity plot. I'm going to drop this dashed line down through velocity so I hit my target correctly. It's going to look like this. All right, so now I have a slope of velocity versus time is negative 9.8 meters per second squared. Oh boy, I did a terrible job there. But that's negative 9.8 meters per second squared. Okay. The slope of this line. This is slowing down, moving upwards. This is speeding up, moving downwards. All right, and this is just the vertical dimension of a projectile. So it's as if we take a ball, we throw it up from our hand, we throw it up in the air, straight up in the air, and then it comes straight back down. And that's our position velocity acceleration relationship in the vertical movement. All right, and it's all because of this equation. And we only have one force acting on that object, and that force is a constant. The force due to gravity acting on the object, okay? We'll do our equations of constant acceleration in just a second on this. All right, so that's the vertical motion. Well, if we look at the horizontal motion, I'll do the same thing, PVA, projectile. Now I'll draw out horizontal position. I'll still use meters versus time. Horizontal velocity, meters per second, 0, positive, negative. And now we're in horizontal, so positive would be moving in the forward direction. So forward is positive. And then I have acceleration, horizontal acceleration, meters per second squared, 0, positive, negative, and time. And now when we look at this equation, forces acting on the object in the horizontal direction, I'll put an H there just to emphasize that. We have mass times the acceleration in the horizontal direction. And in this case, we're dealing with a projectile where we're not dealing with air resistance, and our kinetic analysis looks something like this, our free body diagram. We have one force acting on the object, and it's only in the vertical direction. Therefore, there's no forces acting on the object in the horizontal direction. And so we get an equation that looks like that. Well, mass is not zero. Acceleration has to be zero in order for this equality sign to be true. So therefore, I'll put 3 dots. Acceleration of the center mass in the horizontal direction is 0 meters per second squared. Again, this is a situation where we're not dealing with air resistance, and we have a situation where acceleration is constant, and it's constant at 0. So now if I draw those same hash marks that would correspond with the previous plot, my acceleration is 0. So I'm trying to draw that in there so you can see that. So during flight, the acceleration is 0. Well, now let's deal with the same situation of the projectile flying from the velocity perspective. What does 0 acceleration tells us? It tells us velocity will be constant. And whatever the velocity is at takeoff will be the velocity at landing. So if we throw the object up in the air, we throw a baseball from left field to the shortstop, the horizontal velocity will be constant because acceleration will be 0. So I'm going to draw a situation right now where I'm going to draw a constant velocity, and this is constant positive, and this is an EG, okay, an example. So that's throwing the ball. It releases the hand in the horizontal direction with some velocity, and that velocity will stay constant throughout the entire flight phase. And the way I've drawn this, that means that we have a projectile plot that's going to look like this. I'll do the same hash marks, and it's going to go straight line like that, meaning that it's going to cover some horizontal displacement based upon this velocity. And because the velocity is constant, because the acceleration is 0, and acceleration is 0 because there's no horizontal forces acting on the object. All right, so now let me back up. So that's our PVA, our understanding. And if I, let me just draw, just for sake of completeness, if I draw a constant negative acceleration, then I would have, excuse me, constant negative velocity, then I would have this line here that corresponds with that line that corresponds with the same 0 acceleration. So this is constant negative velocity. Direction of movement would be in the negative direction, and we would start from this position and move backwards. Wow. So we would, if we caught the ball in left field, we'd turn around and throw it into the stands, that type of idea. All right, so those are our PVAs that we're going to need as we start looking at our equations of constant acceleration. Now I'm going to back up from that and actually draw a spatial plot of projectile motion. And I'm going to put X and Y. And so down here we have meters, and on the Y-axis we also have meters. And if I throw an object, if I throw that baseball from left field to shortstop again, and I look at that movement from the side, I'll draw it from this, and we're not dealing with air resistance, this is what our plot would look like. And we would have some change in horizontal motion and change in vertical motion. And remember, what we do is we take that plot and we create 2 plots. We put horizontal motion versus time and vertical motion versus time, and look at each of those. And those are the 2 plots that I just drew in the previous notes. All right. What is also important when we're starting to figure out how high an object goes or how far it travels, we still do this process of taking the XY plot and breaking it into two different graph situations. Now, what we'll often do is we'll take the information from the initial conditions and then ultimately determine some of the projectile motion. I'm actually going to pause for this video, and I'm going to do a part 2 picking up on this situation where we look only at the initial conditions. And I'm going to draw a circle here. I'm going to magnify that down here, X and Y, and this will be just the initial condition, like this, of the projectile. So just looking at this section of the curve at a really fine detail, zooming in on it, we could then figure out this angle of projection, and from that angle we can then figure out initial conditions for velocity in both the X and the Y directions. And then we use those initial conditions to come back to our plots to be able to draw out which line we're actually referring to. All right, so I'm going to pause there, and ultimately I'm going to start doing some of the equations of constant acceleration in the next plot. But this is ultimately where we're going to get to, is look at the initial velocities that are taking place when a projectile begins the flight phase. Okay, I'm going to pause there. Thanks.